Yeah. Hello, class.
Hello.
How are we? We are fine. Good afternoon, precious. Now, I think you are aware that you are now grown-up students of senior 2. That very, very correct?
Yeah.
And we are thinking that you'll behave mathematically like senior 2s. Now in senior 2 we have about 13 topics in math, and that's quite work. I hope that you have changed mathematically from senior 1. Now formally, when we met senior 1, you covered the last topic was time and timetables. Then that would throw us in senior 2 today. Now let me ask this question as I write these topics for senior 2. You think about the question. We last senior 1 ended with we said time and timetables. Then today it calls us into senior 2. Okay. Now have this question answered. When I add, are you listening? When I add 6 to 11, I get 5. How is that possible? When I add 6 to 11, I get 5. How is that possible? Is that possible? How is it possible that I get 5? Let me write these topics of senior 2. Now senior 2 mathematics, as you think about that, in which case is that thing possible? Now term 1, we have mappings and relations. Then 2, these are vectors and translation. Then 3, we are still on term 1, graphs. 4, still term 1, numerical concept 1, in which we have indices and logarithms. Then that ends as term 1. Then term 2, we have inequalities and regions. That's term 2. And regions, inequalities and regions. Then topic 2, algebra 2. Remember we did algebra 1, did we? That was topic what? Then similarities and enlargements. I hope we did the reflection. And the enlargement and translations are a part of that. The circle. Then rotations. Yeah. Then term 3 gets you to length and area, properties of two-dimensional geometric figures. Yeah. 2, nets, areas and volumes of solids. 3, numerical concepts 2, still a continuation of indices, logarithms, and an introduction of surds. Then lastly, set theory. Sets, that's all about sets. That means by the time you count, there are around 13 topics of senior 2. Yeah, this is quite work. That means if you have learned very well your concepts of senior 1, you add on with this, you are growing mathematically. Have you pondered about our question? How can 6 be added to? Yes.
Negative 6 plus 11
equal to 5, but you've created me another question. Mine had positive 6 added to 11. How is that possible? How is it that when I added 6 to 11 I got 5? To you, why? Why did it happen to be so? I got 6, added it to 11, I added 6 hours, I ended up at 5 in the evening. Do you imagine that being correct? From 11 in the morning, if you add 6, you get? Because you see, the question was correct in terms of time. Okay, now I want to switch to the first topic called the mappings and the relations. I think we directly go there. It's quite some work. Now I would ask you this. Did you recall that was under algebra 1 where we saw what we call function machines? There you are. You remember that?
Yes.
Now we shall even talk about it here, applying the concept of mappings and relations. Okay, I would want you to that function machines to be at your head as we speak about mappings and relations. Now under here, since they seem to be two categories of concepts, we shall first talk about one of them, relations. That means we shall visit what's a relation. Yes. And the relations in real life. Then mathematical relations. Mathematical relations. Then representing a relation. I hope you are those at your attention. Now, before that, let me ask you. Let me ask this question. Do you have any sister at home? You have at home a sister? How do you mention what I've asked? How do you answer me back? A sister at home?
Yes, I have a sister.
Yes, you have a sister at home. Do you have anybody else at home? How do you call that person?
My brother.
Now that links you between, that is connecting you and the other person also. How do you call your neighbor here? If we said, speak about who is this girl to you, who is Patience to you?
She's my friend.
Patience is your friend. Now, I want to define what's a relation, but again, we have started with the activity that he mentioned for us the relationship between Patience and her. You are telling us that Patience is my what? My friend. Not so? Is this one also your friend? Now, Patience is my friend. Now, what connects you with Patience is the word my. What is relating you is that you are friends to each what? To each other. Okay, but who is your sister at home? Mention her.
My name is Grace.
Grace is my sister. Then the word is my sister is what is connecting Grace and you, not so? Now this word is what we are calling a what? Therefore, what's a relation to you? Especially, what's a relation? Try.
A relation
Is a set of ordered pairs. Have you connected us here? Connect us.
Patience is related to Ruth in a way that she's her friend.
Therefore, what would be a relation to you? What does this word now mean in terms of these statements? Set of related items. Okay, let us hear.
According to those statements, I think a relation is something that connects two or more things to each other.
Is something or is a link between two or more things. You have a suggestion?
Let me try. The relation is anything that brings two things or more close.
Okay, is anything. Is a link between two or more items or objects, not so? Okay, that's great. We have finished to define what's a relation, a link between two or more objects. Now, examples of relations in real life. Yes, let me have people. Give me some. Yes. A brother. The relation is. Okay. You give us example of a statement. You mentioned the relation and the statement. You have said brother. How do you mention that? Mention maybe something about. Juko is a brother of who?
Patience. Now
Is a brother of
Grace.
Grace.
Yes.
Okay. Now this word is a brother is what we are calling a what? A relation. Are we together? Okay, continue. Give me more. Sister, yes. Continue.
Patience is my sister.
Patience is a sister of who?
Of Ruth.
Of Ruth.
Of Grace.
Could you use that relation is tall and we see?
Patience is taller than Grace.
And patience is taller than Grace. Okay. That's good. That's good. That's good. Yes, you have more?
Teacher, I'm asking, in relations, can we relate like more than two things, like three things?
Yes, we can relate. We can say.
Grace is the fattest amongst us.
Yes, is fatter than who? Ruth and?
Okay.
It's a statement that links two or more objects. Is that very, very right? Yeah. Now, what of some mathematical relations that you could imagine about? Something that is mathematical? Examples of mathematical relations. Yes. Something that has numbers in it. Yes, let me. Okay, you continue, not sir? Yes. Relation, then the example. You tell us what statement is going to link, then you mention an example, yes? You were ready? Or you've changed the mind?
Multiple.
Yeah, yes. Something can be a multiple of the other, like mention who is who.
9 is a multiple.
9 is a multiple of 3. That's very, very great. Multiple of is what we are calling a relation. Square. Then 16 is
a square of 4.
the square of 4. That's great. Let me even numbers. How do you connect?
Even numbers.
Connect as long as you develop. Okay.
Okay, so I have another one. Okay, I'm not very sure.
Be sure now.
So let me first try. Wait to write.
Okay, first discuss with them. Is it whether it will be correct or wrong?
Okay, mine is not like multiple square. It's kind of a number. It's like n plus 2 into brackets power like 2. Now they're related because of this.
What it mean this? It means the square. I'm thinking also like Precious told us. Factor of. Who is the factor of who? What are you? Who is the factor of the other? 2 is the factor of 4. Yeah. That's good. That's good. That yes.
I'm just asking. If it's like negative 3, then times negative 3 equals 2.
That means negative is a square of, not so? Is a square of. You pick that because multiplying a number by itself is squaring it, not so? Yeah. Okay. You have something? Okay. Let us go to how do you represent a relation? Representing a relation. Hope you have. Do you have a circular? That's a compass representing a relation. Now we can represent it using what we call a parallelogram. and also using what we call ordered pairs. Now, what do we mean by a papagram? Like if we took your table there to be a place where we sit only people who are related, how do we draw arrows? Like maybe our relation using a papagram, maybe before we can discuss about a papagram, and I wanted to connect all of you. Maybe I can connect you using height is taller than, like which arrow do you draw now is taller than? That means you would say? The arrow is taller than the other. Patience is taller than, the arrow moves from where you are going is taller than. That means you would draw, or we would tie a string from here, taller than. Then how do we connect this?
Patience is taller than. So I think connect from this one to this one then.
Isn't you taller than this one?
No, we can't draw an arrow like close to this one.
But pointing some direction.
Yes.
Yeah. And now a papagram is just a circular representation of a relation. Circular representation of a relation. For example, we can if you add these we say who is taller than the other? Who is taller than both of you? Using the relation is taller. Draw a papagram to show. Now we want to show a link between you guys who are in class. Is that word correct, guys? What guys refer to a man or both?
Both.
Is taller than to draw, is using the rest is taller than draw a papagram for the following set. Who is taller than the other?
Patience is taller than.
Patience is taller than Ruth and then Precious.
Precious is taller than Grace.
Precious is taller than who?
Grace.
Taller than Grace. Then Ruth is taller than who? The shortest.
The shortest is this one.
Is Grace.
This Grace.
Ruth is the shortest, not so?
No, Grace is the shortest.
Okay. Now, how are we representing that? Now we are drawing a papagram. A papagram, you just draw a cyclic set. Then put in the members. I have here our Ruth, not so? We have also. Who also do you have? Precious and there is this other Precious. And Millie, not so? Precious is taller than Grace. What of Millie? We didn't mention Millie here. Millie is taller than who? Taller than Patience?
Yes. We know what I've seen. Let's measure.
Okay. How would we connect Ruth? Mire is taller than? Mire, I think, is the tallest. Mire is taller than this. The same Mire is taller than. You see the arrow moves from where is to. Yes?
Yeah, I want to indicate Patience. So remove Precious.
Precious. This is Patience. That means, whom are we removing here?
Teacher, it's Patience, not Patience.
Who is this one? This is Ruth. Ruth is taller than?
Grace.
Where is Millie is here? Okay, we go on.
It's Patience.
Patience, where?
You're very patient.
This is Patience. Like this, eh? Like AC, not so? Okay, we connect. Mire is taller than?
Grace is the shortest.
Who is the shortest?
Grace. Tell the way look short.
Grace.
The last statement.
Grace is the shortest.
Yes.
Now we continue. Patience is taller than who?
Then Ruth.
Taller than Ruth.
Taller than
Taller than
Grace.
Grace.
And Ruth is taller than Grace.
Ruth is taller than Grace. Yeah. That's the cyclic representation of the what? The papagram. The relation. Okay, remove that. I've removed that. We go on, not so. Let me put some mathematical relations here. Have you captured this? I want to put some mathematical ones here. Precious, you okay? Okay. Could you give us a set of counting numbers?
1, 2.
Counting numbers. That's 1,
2,
3, 4,
5, 6,
7, 8,
9,
10. Not so?
Yes.
Yeah. Use the relation A. Which relation can we put between those elements? Get for me one relation there that we can. Yes.
10 is greater than 9.
That means your relation we are using is what? Greater than. What other relation? I think we are going to have that there. Is?
Less than.
Wouldn't it mean the opposite?
Is equal to. Teacher.
Sure.
Is a factor or amount or.
Is a factor of. You can ask your question.
About the other topic.
Yes.
Since Miri is the leftoist or bus, why don't you?
Not so.
Meaning lines can even cross each other.
They can cross it. The lines can cross each other. Now we are here is greater than. Who is we feed in the that's 1, 2, 3, 4, 6, 7, 8, 9, 10. It can be anywhere. Who is greater than the other?
10 is greater than
all, 10 is all, 10 is greater. Not so?
Yes.
Then what else?
9 is greater than 1 to 8.
9 is greater than 1 to
8.
The lines are going to be very, very many, not so?
Yes. 8 is greater than 1 to 7.
That's...
I think we could have done from 1 to 5 minutes. Yes.
But you gave me a relation which is a bit terrible.
Actually,
Could you give me a match, a one that has few elements in it? Is
5 multiple.
multiple. Multiple of, you are sure that's small? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who is the multiple of the other? 10 will be for all.
Yes.
Okay, go on. 10 is a multiple of 2, 5. Only 4 is a multiple of, and also 5 is a multiple of 1 only. 5 is a multiple of 1. Still, this one made it. 6 is a multiple of 1. 7 is a multiple of 1. Multiple of 1, multiple of 1. And 9 is a multiple of?
8 is a multiple.
That means you'll fill up everything, not so? Is a factor of, think about that, is a factor of?
1 is a factor of all.
Out of itself? Themselves, not so? Each is a factor of itself. That means draw a closed circle first before you add it to each. Not so? Then 1 is a factor of? That's again going to be too much. This one should not be put in sets. Do you advise that? Then who is a factor of the other?
2 is a factor of 4 and 8 and 6, 8 and 10.
And 10.
Yes. 3 is a factor of 6 and 9.
Then
4 is a factor of 8. 5 is a factor of 10.
5 is a factor of 10.
6 is a factor of
Aisha, itself.
8. 7, 8.
That's finished. Not so? Yeah. I think
Do they bring these relations in exams? Because I can get confused.
now let us ask that what is the purpose of studying relations?
In real life.
And what is now the purpose of us studying these relations? Because he's complaining that do they come in the exam?
If it's in real life, relations, yeah, school, eh? Now you see them say like a distant relative wants to property. Relations can help you.
Yes.
For me, I think he agrees with them. They learn relations just to know the connection between them.
And you yourself, see?
Yeah, but then why should they bring them exams? Otherwise, we
Because they are important. They are important. Therefore, We set them. We set them. That's yet to be decided by the UNEB. That very right. Yeah, now I think you have captured that. We want to shift on. I would like for somebody to connect, to draw a papigram for a relation speaking about is a square of. That means that's the last we can have a student taking on that. Then we shift to another form called ordered pairs. Okay, represent the set. The set A equal to 2, 4, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Using the relation is a square of. Can we have one student taking on that? Then we shift. Is a square of. Patience, you seem to be very ready. Are you? You are ready. Run in 2 minutes and.
So the question is using the relation is a square of, and they want us to draw. So you have to draw a circle. Then you have to put in those numbers. So, square, it means multiply yourself, right? So 2 times 2 will give you 4. Then 3 times 3 will give you 9. 4 times 4, 16. It's not there. 5 times 5 is not there. 6 times 6 is not there. 7 times 7, 8 times 8, 9 times 9, 10 times 10, 10 times 0, 2 times.
Have you explained it very well? Okay. Okay, thank you. Thank you, Patience. Yeah. This is, you are correct. That's all? 2 is the square of 4. Yeah. Yeah, we can go on. Have you captured this? I've seen Grace is really absorbing things at a very high. Are you absorbing your math very well? Now, are you absorbing your math very well? Okay. Patience. Let us continue. Patience, are you okay? Okay, let us shift it to the mappings. Yes.
We haven't spoken about the ordered pairs.
Order D. Oh, that was part B of representing okay. Using order D. It means you are very, very attentive. Okay. Okay. Now, Ruth, what's happening? Okay, now we can connect two sets, like if, for example, I have 2, 4, and 6. I can develop another set, multiply by, say, 3. If I multiply this set by 3, what do I get? Multiply by 3? 6. Gives me 12. 18. That means I can connect 2 to 6 and 4 to 12, 6 to 18 using a relation. Multiply by 3. Okay, give me another connection between using that. Give me another connection and we develop ordered pairs. Yes.
10.
Which set are you giving me? 10? 8. 6. Those are enough. You are connecting them by divided by 2. Therefore, we'll have 4, 3. What is the ordered pair?
10, 5.
That pair is 10, 5,
8, 4.
8, 4,
6, 3.
6, 3.
Using a relation.
ETC using relation divide by 2. I've not heard from who? Mira, you're very, very quiet. What's happening today, Mira? Okay, give us the other last relation and we connect. Then we jump to mappings. Yes, Ruth. Which relation here can we use to create ordered pair? Relation is? Square. That means you have this set called negative 3, negative 2, and 1. Square them, you get 9, 4, 1. Ordered pairs,
Negative 3 and 9.
3, 9,
Negative 2 and 4.
2, 4,
And 1, 1.
1, 1. Yeah, thank you.
Foundation square.
Yes. What connects the two sets? You're squaring, not so? Square, thank you very much. Grace, for being very, very attentive. I love that. You also love that? I love attention. Now, let me shift very fast to mappings. Any question in relations? Any question? Relation?
Can you also subtract maybe the order?
As long as you can connect two items by anything, by subtraction, by getting square root. That's all. You're asking a question, Grace?
I just wanted to ask whether connecting something to the other. Do we have to just base on their data format, multiplying, dividing, addition, subtraction?
Now, me then I will ask, how is your mother related to you? Can we develop an ordered pair between you and the mother? Grace and the mother. What relation can connect you and your mother?
Grace is my mother's look. And even they are both women, I mean ladies.
That means we can create an ordered pair there by putting you and the mother in the same bracket using maybe, if your mom is called, she's called what? Grace also. Agnes produced. Therefore we can connect, like we can say Agnes produced who? Produced which girls? Grace and who?
And
Ruth.
And Patience.
Patience. Now that means your ordered pair will be Agnes with who? Grace. Agnes with? Agnes with Patience.
Agnes with me.
And finally using which relation? Produced. Not so? And that means we don't have a relation will depend on the set given, will depend on the items that we are talking about. That very, very right. Now, let us talk about mappings. Are you there?
Yeah.
Now, all through, I want you to be very, very attentive. Be very, very attentive. Very, very attentive. What is to map? What is to map in English?
To map is to draw an actual object as seen from above.
Say it again.
To map in English is to draw an actual object as seen from above.
Let me leave that standing in air. Yeah, I saw your hand, not so? No. You have a suggestion? No. Anything? No. Now she said to map is to draw something from something. But for us here, we are just going to see that to map is to transform something into something. Into something, not so? Now look here. 2 can be made 4 by which operation? Now we are simply saying that we are simply maintaining the fact that even though you are talking about a mapping, we are still talking about a relationship. I don't know that you're picking. 2 is connected to 4 by some rule, not so? What are we trying to do to get 4? That means a mapping is a relation which transforms objects from one set to another, which takes objects from one set to another. That's just an operation. Is a relation which takes objects or elements from one set to another set using a certain rule. Using a certain rule. Okay. I think that's pretty understood. Now, I want you to really be very, very attentive. We are saying 2 can be made 4. Which rule is that? It's like you have multiplied 2 by. Now, 6 can also be made 12. The same rule that we are applying here can work here. That if I call the 2x, what am I doing to x to get 4? Am I saying plus 2? Will it work here? X plus 2, will it work? X times 2. 2 times x, and our x is 2. 2 times 2 gives and x is 6. 2 times 6, 12. Now listen, this side having 2 and 6 stands for what we call the objects. Then the other side gives us what we call their images. Now the objects are also given a name called what? Then these are called the range. Is that very, very right? Now that a mapping takes objects from one set to another, it's just a relation taking elements from one set to another. I want to give you this question about the relation. You first see, but before I give you that, we should acknowledge that mappings can be represented by using simple equations and arrow diagrams. What can you map in real life? Representing a mapping, we can use an equation, and we can use arrow diagrams. For example, an equation, we can say x gives us x gives us 4. X gives us 4x. Okay. Using equations to represent mapping. Now, if you had such a mapping, x gets us to x plus 1. Our set here stands for x values. Now it shows that these values have to be made to x plus 1. Now each value here is standing for a value of what? x being transformed into 2x plus 1. Yes. Now if we are to work out the first x value is negative 1. But our mapping is simple that x go to 2x plus. Therefore this negative 1 will go to 2 times negative 1 plus 1, which is negative 2 plus 1, giving us positive 1. Positive 1. Then the next x value is 0. How shall we arrive? 0 gives us plus 1, which is giving us 1. When x is 1, 1 gives us 2 times 1 plus 1, which is 2 plus 1, 3. X gives us 2 plus 1, which is 4 plus 1, giving us 5. Now, what we've got here, these elements are called the range, and the given set is called the domain. We have a domain getting us the range. New elements are called the what? The range. That means our range is now having negative 1, 1, 3, and 5. Okay. Let me capture here one number and people can do for us. That's how we can represent using an equation, but now we also can use the arrow diagrams. Diagrams. Let me just capture this. I hope you are warming up to do numbers, not so?
Yes.
Yeah. Any question on equations, representation?
Excuse me.
Yes, excuse me.
Does it mean if maybe that question is brought in exams, they give you
The domain,
they give even the formula of getting
the mapping is given, and the domain. Or else we can give you the range and we would like to have the domain with, we give you the mapping and this. Then we want you to get back at the domain, which I believe you can. You perform the reverse operations where there is division u. Now using arrow diagram, did we meet something of the sort? To represent a mapping, we can pick that same let's see, negative 2, negative 1, 0 and 1. Okay. Are we right here? Now I want to find out the elements. I think you'll guide me, won't you? Are you guiding me about it? Yes, guide, and we see how should we arrive our set P. Negative 2, negative 1, 0, 1. X maps onto 2x. The first domain is negative 2. Negative 2 gives us negative 4. When x is negative 1,
2 times negative 1
gives us negative 2. When x is 0, 0 gives us. Then when x is 1,
2 times 1
gives us 2. Not so? Now look, our arrow diagram can be drawn in two ways. Arrow diagram. We can have one set here, and then draw I think uniform figures very well. Okay, I hope that's okay. X gave us 2x, not so? These original elements are called the domain. These are called the range. What's my domain?
negative 2
Negative 1, 0. My range?
negative 4 negative 2 0 and 2.
0 and 2. This is mapped onto. You understand?
Yes.
Yeah, that's the arrow diagram.
Teacher, like you taught us in the senior one, can we also use it?
Yes, that's another form. This one you can use this or use the other number line elements for the domain and for the people are ready to discuss for me these two numbers. Alternatively, somebody can use this arrow diagram and put here some elements. This is still our domain, and this is our range, not so? I'm running from negative 2 to 1, 0, 1, not so? Then here I will have negative 4, negative 3, negative 2,
negative 1 0 1
1 and 2. This one is mapped onto
negative 4
and negative 4 here.
negative 2
Then 0 goes to 0.
negative 1 to 2 positive 1
Yeah. Okay, let me put for you some numbers here and are we together? I want to give you something here. Oh no. Yes, draw. This is example 3. Who is warming up? All of you? The mapping x gives x squared. State the ordered pairs. Okay, who has warmed up, and you take on that. Precious, Ruth, you have warmed up. You explain as clear as what?
The question says this is the mapping x represents x squared on the set -2, -1, 0, 1, and 2. Work out the elements of the range. So x represents x squared. So this x is -2 for the first one, which represents x, since it's x is -2, -2 squared. So -2 times -2, which is -4. No, +4. Then -1, x, which is representing -1, so -1 squared, -1 times -1, which is equals to +1. Then the next is 0, x is representing 0, so 0 squared. 0 times 0 equals to 0. Then the next is 1. X represents 1, so 1, as I said, x squared, 1 squared, which is equals to 1 times 1, which is equals to 1. Then the next is 2. 2 squared. Since this is 2 represents, x represents 2. So x squared, which is the same as 2 squared. So 2 times 2, which is equals to 4. So we've already found the elements. We've worked out the elements of the range, which are +2, which is +4, which are +4. +1, 0, +1, and +4.
You don't repeat.
You don't repeat. What's so many before 1, 2?
I don't repeat. Okay, then B is saying state the ordered pairs. The ordered pairs are, the first one are -2, in brackets -2, and +4. Then the second one is -1 and +1. Then the third, 0 and 0. Then the fourth are 1, 1 and 1. Then the last are 2 and 4. Then question, should I ask you?
This one?
Then question C states, represent the mapping on an arrow diagram. So I can either use this or a number line, but I've decided to use this method, which is -2, -1, 0, 1, and then 2. Then this side it is +4, +1, 0, 1, and 4.
Don't repeat.
So it will end at 0, 4, 1, 2. And then, okay,
You want her to help you? Please help.
since we're already given 4 2 times and 1, so I have 4, 0, no, 4, 1, and 0. So -2, since it is paired with 4, so the arrow will go to 4. Then -1 with +1. Then 0 with 0. Then +1 with still this very same one, so they'll all direct to that one. Then +2 with this 4.
Yeah, that's very, very wonderful. This is the domain. This is the range. X gave us x squared. Thank you very much. Now, I hope you have seen that in one set, one element can go to one element, -2 goes to 4 as well as 2 goes to 4. Now, we are switching on to what we are calling here types of mappings. We have said don't repeat a set, don't repeat the range. In fact, your range that you should have written was 4, 0, 1, and what? And 4. You don't repeat the elements. Now here, look here. See, you see that -2 went to 4, 2 also went to. Now look here, we are now discussing types of mappings. 1 to 1, 1 to 2. Now me, I will pause there and people add me the rest. There is 1 to 1 where you have every member having corresponding with exactly the same. A will give a different answer. This one also gives its own answer. This one gives its own what? Answer. But look here. This gave the same, this gave the same. Which type of mapping could we categorize that?
1 to 1.
Huh? We still have more. Is this 1 to many? These are now 2 to 1. That means we can have it as many to 1. What will be the other last one?
2 to 1.
No, 2 to 1 would be many, yes, many to many. Okay. Let us start with one-to-one mapping, and I'm requesting for somebody to define for us which type of mapping is that. Yes, Grace.
One-to-one mapping is a type of mapping where each domain has its own range.
Where every element in the domain corresponds to only one element in the range. Clear?
Yes. One to many. This is the
You are going to define, you are defining one to many?
Yes.
That means here you have D, E, and each answer is different. Define now one to many.
This is the type of mapping where two or more domains are corresponding to one range.
Where remember you are defining one to many. Yes, Patience.
Many mapping is a type of mapping where one domain is corresponding to many ranges.
One element here is giving different answers. Like this can give a D and F, then you can have B also giving E and G. You want to define for us? Many to one.
It's the type of mapping where the domain is
where one element in the domain corresponds to.
Where many elements in the domain correspond to one in the mapping. Just like that.
Just like this one. This is a many to one mapping. Many correspond to one. Thank you. Then I will need the many to many. Yeah, you've told me many to one. Mapping is the one in which more than one element in the domain corresponds to only one element in the range. Okay?
Many to many mapping is where the type of mapping where the domain and the range correspond to many elements. Where many domain correspond to many elements in the range. Many elements.
Like this can go to that, as well as this can also go to. There is a mix-up.
Yes.
Okay. Now I want people to prepare. This time I want really to come and you work out to even tell us the type of mapping. Okay, let me quote here. Grace, you are comfortable with the work? We put for you a question. Now it is a set A maps onto set B by the operation a set A maps onto set B by the operation multiply by 3 and add 1. If set A has the elements, 5, 6, 7 and 8, work out, that's part A, work out the elements for the range, open bracket set B, work out the elements for the range set B. Then part B, represent the mapping on an arrow diagram. Then part C, state the type of mapping. Are we already there? We said we are having who? You'll be very audible.
We are going to get 5 times 1 theory plus 1, which is equals to 15 plus 1 equals to 16. Then we shall get 6 times 1 theory plus 1, which is equals to 18 plus 1 equals to 19. Then we shall get 7 times 1 theory plus 1 equals 21 plus 1 equals to 22. Then 8 times 1 theory plus 1, which is equals to 24 plus 1, which is equals to 25.
Thank you, Mire. Now I would like to take on another student. A mapping is defined by the ordered pairs -1, 2, -1, 2, 4, 6, 5, 0, and 4, 3. Part A, represent the mapping on an arrow diagram. Then state the type of mapping. That's -1, 2. The next one was 4, 6,
5, 0,
and 4, 3. Present on an arrow diagram. Yes, who has not felt the class for a long time? Yes, somebody rush on and handle it.
Okay, representing it on the arrow diagram, we have -1 on the domains. Then we have 4. We have 5. Since we already have this 4, so we shall not indicate this other 4. And then on the range we have 2, we have 6, we have 0, and then 3. So the 1 corresponds to these 2, the 4 will be 6, then 5 with 0, then 4 again with 3. And then the type of mapping, this is many, no, 1 to many.
Thank you, very, very fantastic. 1 to many. Okay, now I've finished up with mappings. I think people are now aware, not so? Okay, we switch on to functions. Now, why? You see, listen, our topic was mappings and relations. But there is something here. When a mapping is 1 to 1, listen, it is given another name called, when a mapping becomes 1 to 1 only, then it can also be called a function. See that? That's very correct. A function is just an operation that makes sure one thing gets another new thing. Because of course, if you build the meaning of function from English, that carries meaning to you. Now let us drop to functions, because we cannot go without talking about them, because remember that we met them in function machines. You remember that?
Yes.
Okay, you can write a function now. It is a 1 to 1 mapping in simple terms. A function is just now a 1 to 1 mapping. Yeah. Have we captured the meaning of a function?
Yes.
What is a function?
A function is a 1 to 1
Okay. Now, test your head with this. Given the mapping, x gives 2x using the domain -2, 0, 1. State whether the mapping is a function or not. Let me see somebody guide there. How shall we state? Is it a function or not?
We shall have to first find.
There is this patience is warming up. Okay. Discuss it very, very properly.
Yeah, so the mapping is x to 2x. So this x represents like this number. So x is -2. So -2 times -2. That is equal to negative. So we go to 0. 0, 2 times 0 equals to 3. We go to the next one, which is 1. 2 times 1 equals to 1. So we have to state whether the mapping is a function. So we have to first find out if it's a one-to-one mapping. So this is -2, 0, and +1. So here I have -4, 0, and +1. So the mapping, therefore, the mapping is a function.
She has been very, very superb. You love that like I do. Now, representing a mapping, which we call, a function. Yes, how do we now represent a function? Somebody recalled some work that we talked about? Yes, representing a function. We use, what are the ways? It's called the function notation. How do we represent a function? Somebody guide us. The first item is using an equation. E.g., we can have it as y is equal to x plus. Of course, an arrow diagram would tell that it is a one-to-one or not. If it's a one-to-one, you know what it means. Then using a function machine. Yes. Then yes, can be a mapping like one-to-one as we've been seeing using. And must be what? 1 to 2. Okay. Okay, now let me start with the... Okay, that means I can start with an equation, then we break it into a function machine, then we break it into... Okay. Now, sometimes instead of calling it y is this, we can call it fx is equal to x plus. The same thing, not so? Now, examples, we test ourselves, not so? Given the function fx equal to 2x plus 1, work out f of 2, f of -1, how do you develop that? How do you... Now, you see, when they say, when it is fx is equal to x plus 1, that simply means if you say f of 2, the place of x has taken what? That means 2 times 2 plus, which is 4 plus, giving us Okay, you work out this other one. I want the answer mentioned to me, part B. Yes, part B, work out. You've already worked out? F of -1 is -1. Okay. Okay. I want to shift to now I'll just test this other one, a function. This is example 2. Function is represented by an equation y is equal to 1 minus 2x. Seeing I would need help because I'm defeated. Do you believe so? Somebody come and help me, guide me very, very well there. Yes, Grace, you can. Warmly guide the teacher because the teacher is defeated. Can you see?
Okay, working out the missing values in the table. For the first column, we are missing the value of y. And as it will say, the function is y is equal to 1 minus 2x. So we are given 2x as negative, we are given x as -1. So it will be y is equal to 1 minus 2 times -1. And therefore 1 will give us 1 minus -2. And then 1 will give us a positive, a negative times a negative, positive. So it will be 1 plus 2, giving us y is equal to 3. So again, we're missing for the next column 1, so it will be y is equal to 1 minus 2x. So y is equal to 1 minus 2 times 0. So this will give us y is equal to 1 minus 0. Cos 2 times 0 is 0, so it will give us y is equal to 1. So for the next one, still we are missing out y. So it will be y is equal to 1 minus 2x. Y is equal to 1 minus 2 times 1 for the x. And then y is equal to 1 minus 2 times x. 2 times 1 gives you 2. So it will give us -1 since this 2 is a negative. And then for the next column, the last one, we are missing x. So to find x, you'll have to interchange it the other way around. So it will be 1 minus 2x is equal to y. So 1 minus 2x equals to -3. So since this one is a positive,
is a positive, we shall subtract 1 on both sides. So we shall have 1 minus 1 minus 2x is equal to negative 3 minus 1. So it will give me 2x is equal to negative 4. We divide both sides by negative 2 to give us 2. So x is equal to 2. So now represent the function as a mapping. Since this is a one-to-one mapping, so it shall just be like the previous mapping. So we have x for x and then for y. This can also be called the dominion, then this one can be called the range. This is negative 1.
The domain.
And then 0, 1, 2, and 2. Then for the range we have 3, 1, negative 1, negative 3. So here we have 3, 1, negative 1, and then negative 3. And this is for y. So this negative 1 is then 3, 0 is 1, then positive 1 is negative 1, then 2 is negative 3.
Yeah, thank you very, very much. That's good. I think that is pretty good. That's pretty good. Now we are switching to using a function machine to represent functions. You are there? But we visited that one in algebra 1, not so? Yeah. I think can we flow with you okay, Grace, with that? Okay. Let me flow with using function machines to represent functions. Using function machines to represent functions. Now there, we can just see from this example that if one is this, let me make it much better first and simpler. 2x plus 1 we have where we are feeding in, but the first operation we are doing is we are multiplying by times x multiplied by 2 first, then followed by plus 1 to give us y. That means, like if I had some x values, maybe my x 0, 1 and 2, what will my function machine produce?
1.
0 times 2
0
plus 1 is 1.
Yes.
Then 1 times 2,
2 plus 1
3.
times 2 plus 1 5.
5. I think that's pretty easy. You can even draw the mapping diagram.
Yes.
Yeah. Now I want you to, this is just a review because we did it under algebra 1.
Yes.
That means I want you to use you convert this one to a function machine, write the equation. A function is given by that. Write down an expression. Represent it on a what? On a function machine. Then work out the values of y. Who could try? Give it a thought. Give it a thought, somebody. Give it a thought. I want this to be now in this format. You want to give it a thought?
X equals to minus 2.
X equal to, what are you doing?
You're going to
What are you doing to x?
To multiply it.
Negative 2 times negative 2. Then what are you doing to next?
Plus 1.
Plus or minus 1?
Plus 1.
You are simply saying this one can be written as negative 2x plus.
Yes, this one is a positive.
This is the same, which is this. Then patience give us the what? This other domain. In case we have that set, what should we have?
So we will have x 0 times negative 2 plus 1 is equal to 1.
1. The next
1 times negative 2. Negative 2 plus 1.
is
Negative 1.
negative 1. Then
2 times negative 2. Negative 4 plus 1. Negative 3.
okay, now students, we cannot do beyond that, but as a closure, to just find out whether people have picked. In case you had given a function machine of this format, then plus 4 minus 3. What is the output here? If you fed in a 7, the function machine work out the output for for 7. 7 is entered there. You get here you produce 8.
Yes.
Yeah, now class, I want to thank you for attending, and that's the first topic in senior 2. It's mappings and relations, but we divided into mappings and relation, then we finally looked at functions as a mapping. Now when we looked at the relations, we defined it, not so?
Yes.
And represented the relation using ordered pair and a parallelogram. Somebody recalls? Yes. Then from there we shifted to the mappings. We defined the mapping. Then we listed the types of mappings, and which threw us to a one-to-one mapping that was called a function. And there we are with the topic closed. Thank you. We meet in the next topic 2 called the translations and vectors. You wanted to ask a question?
And sort of the activity of interpretation.
Activity will come in later. Thank you.